In this video, we're going to discuss enthalpies of formation as a means to calculate Hess laws. So if we have a reaction, as we do up at top, that we want to find the delta H for, well, what happens if we don't have a series of reactions that we can sum together to achieve it? There is another route that can solve Hess laws. This is using what's called a delta H of formation. Delta H formations are actually values for equations, but they are very specifically built. A delta H of formation is always designed as making 1 mole of a molecule and is done from elemental starting materials. What this means is if you have something like water as a product, well, to make specifically 1 mole of product molecule and nothing else, you make it from exactly the right amount of elemental starting materials, which would be, well, 1 mole of H2 will give me the 2 hydrogens, half a mole of dioxygen will give me the full mole of oxygen I need. This is how you would write the delta H of formation for liquid water. The enthalpy of this reaction is written as the delta H of formation of water liquid, and it happens to be, as is indicated over here, negative 285.8 kilojoules. To do this reaction would give off 285.8 kilojoules. We started from elemental starting materials. Since all delta H of formation values begin from elemental starting materials, they all have a similar origin point. This lets us shortcut Hess's law. Instead of long, complicated reactions between wildly different molecules, everything comes from just the same few starting molecules. Hydrogens, oxygens, carbons, chlorine gas, anything else, they come from the same elemental sources. The delta H of the reaction you can either get by many different equations summed together, or you could get it from the delta H of formation values. The sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Because delta H formation hides the fact it really is an equation, we can actually simplify these. We don't have to write all the equations out. We can just use the enthalpies of the formation values. So if we want to look at this reaction up above, what do I really have? Well, I have HCl aqueous, and I have a value for that. I have sodium hydroxide aqueous, but I don't have a value for that. What I do have is sodium aqueous and hydroxide aqueous, which, if you dissolve a salt, it tends to separate. Sodium hydroxide is a well-dissolving salt. This is really a sodium ion aqueous plus a hydroxide ion aqueous. This is part of our ionic reactions. They have separated once they are in water, and I do have values for those. So there is no value for sodium hydroxide aqueous. There is a value for the sodium and the hydroxide separately. This is going to affect our products as well. Over here I have sodium chloride aqueous, but what I really have is a sodium aqueous and a chloride aqueous. Once we've identified what's in our reactions, I can sum them together. What is the delta H of my reaction overall? Well, let's look at the products. My products are over here. What do I have in my products? I have a sodium. I have 1 of it. So I go find the sodium amount and just put in 1 of it. So 1 times negative 239.7 kilojoules. It's written as kilojoules per mole. We have 1 mole, so really those will cancel out when we multiply those. Well, that's for the sodium. I also need to do this for the chloride. There's 1 mole of chloride times the chloride ions minus 167.5 kilojoules per mole. And I have liquid water, so plus the liquid water, which is, well, again, 1 mole of it in our balanced reaction, times negative 285.8 kilojoules per mole. That is going to give us the delta H of formation of the products. Now, we haven't finished. We now need to do the reactants, but let's simplify what we're writing here a little bit. Negative 239.7 plus negative 167.5 plus negative 285.8. Negative 693 kilojoules is over here for our products. I need to subtract our reactants from it. What are our reactants? Well, I've got HCl aqueous. I have 1 mole of the HCl aqueous, and we said that is minus 167.5 kilojoules per mole. Plus, next was sodium. 1 mole of sodium ions at negative 239.7 kilojoules per mole, plus 1 mole of hydroxide, which was negative 229.9 kilojoules per mole. So I can find the sum of my delta H of formation of my reactants. Negative 167.5 plus negative 239.7 plus negative 229.9. Negative 637.1 kilojoules. So what is my delta H of this reaction? Negative 55.9 kilojoules, or negative 56 kilojoules. Some of these values were the same on both sides, you may have noticed, but that's because, well, once our sodium was dissolved, no reaction happened. If we actually think about what's occurring up above, sodium hydroxide had already separated. The sodium did nothing in this reaction. It was really just H plus and Cl minus. So we had to deal with the HCl breaking apart, Cl then becoming a free-floating ion. The H plus and the hydroxide had to eliminate each other. So some of the things we saw were canceled out. Our sodium on both sides really didn't affect our calculation. But the things that were different, the hydroxides and the like, ended up giving us our final value. If you have the delta H of formations for each of the chemicals in your target reaction, you can simply sum all of the products and then subtract the sum of all of the reactants. This will also give you the delta H of your reaction. This is often far easier than a regular Hess law. If you have the chemicals and can do this, this is a very effective means for calculating out the enthalpy of a reaction. To obtain it, there are tables of standard enthalpy of formations. You can find them in the back of your book. You can also find them on Wikipedia. Just look up standard enthalpies of formations. There's excellent tables of values. Let's do one more. Fe2O3 solid plus 2 aluminum solid goes to 2Fe solid and aluminum to O3 solid. Now we could construct this from a variety of different reactions, or we can just look up the delta H of formations of each chemical. Fe2O3 solid is negative 822.2 kilojoules per mole. And for Al2O3 solid, it is negative 1,669.8 kilojoules per mole. And those are the only two we need. Because if we think about iron or aluminum on its own for a second, if my product is going to be iron solid, well, what elemental source of iron is there on Earth? Iron solid. Since aluminum solid and iron solid are the elemental forms of those metals, there's no delta H. The delta H of formation for an element is 0. And so we really only have 2 delta H of formation values. Well, that means my products minus my reactants. My delta H for this reaction is going to equal negative 1669.8 kilojoules per mole and 1 mole. So just that many kilojoules minus negative 822.2 kilojoules per mole and, well, 1 mole again. The delta H of this reaction then is negative 847.6 kilojoules. If we want to think about this, what are we really doing when we have our products minus our reactants? Because there is another way we can think about this. Delta H of formation of Fe2O3 would involve iron solid and O2 going to Fe2O3. I'd need 2 irons and 3/2 O2. This would be the equation for the formation of our iron 3 oxide. So this would have a delta H equal to negative 822.2. Well, you could also write a reaction for the delta H of formation of the aluminum 3 oxide. It'd be 2 aluminum solid plus 3/2 O2 going to Al2O3 solid. This has its own delta H, negative 1669.8 kilojoules. Our delta H of formation values, remember, come from a reaction. We can write what that reaction is. If we then just call those reactions A and B, we can modify these to create the original reaction that we want. Well, Fe2O3 needs to be on the left, it's on the right, so I have to flip A. So flip A around to get Fe2O3 solid goes to 2Fe solid plus 3/2 O2 gas with a delta H equal to positive 822.2. Well, my aluminum Al2O3 is already on the correct side and the correct amount. I just need to sum our modified A and B. What will happen is 2/3 of O2 will cancel. I will get Fe2O3 solid plus 2Al solid goes to 2Fe solid and Al2O3 solid. I can use the formation equations to actually create our target equation. When I go to add these, what I've effectively done is I've taken the delta H of reaction B, just as it was, and I'm adding the negative of what reaction A was. Well, adding a negative is subtracting. Effectively, I have delta H of reaction B minus delta H of reaction A. And what was reaction B? It was the delta H of formation of aluminum oxide. So really what I have is the delta H of formation of my product minus the delta H of formation of my reactant. This is Hess law. It's just done with a standardized set of reactions. Instead of any random reaction, it is a standard set that compares everything to its elemental starting materials. This means I don't have to find a dozen different reactions that make all sorts of intermediates. I don't need reactions that involve chemicals that aren't even part of my target reaction. I can simply use the chemicals in my reaction. Delta H formation calculations vastly simplify the work necessary to calculate a Hess law when we are able to use them. New chemicals that somebody invents might not be able to have this process be done, but the vast majority of reactions, we can simply use the delta H formation values to calculate out the enthalpy of the reaction we want.